I am Amrita from Department of Electronics and Communication Engineering, and my Tech Talk topic for antenna and wave propagation is electromagnetic cloak. Introduction to electromagnetic cloak. Electromagnetic cloaking aims to make objects invisible to electromagnetic waves. It involves manipulating light and other electromagnetic signals to avoid detection. This technology has potential applications in defense, privacy, and scientific research. This electromagnetic cloaking make the objects invisible to electromagnetic waves. So object becomes invisible to the electromagnetic waves. Historical background. The concept of cloaking has roots in science fiction and theoretical physics. Early research gained momentum with the development of metamaterials. The first practical electromagnetic cloak was demonstrated around 2006. Basic principles of electromagnetic cloaking. Cloaking relies on controlling the path of electromagnetic waves around an object. This is achieved through materials with unique electromagnetic properties. The goal is to minimize scattering and reflection, rendering the object invisible. So, coming to the basic principles, the object around the object, the electromagnetic waves will become invisible. So that this is achieved with the different types of electromagnetic properties which are not same. And the main goal is to minimize the reflection and scattering. Hence, the object becomes the invisible. Electromagnetic spectrum and cloaking. Cloaking can be designed for different parts of the electromagnetic spectrum. Visible light cloaking is more challenging than microwave or radio frequency cloaking. Most current cloaks operate, hence, cloaking can be designed for different parts of the electromagnetic spectrum, where the visible light cloaking is more challenging than microwave or radio frequency cloaking. Most current cloaks operate effectively at microwave frequency. Metamaterials in cloaking. Metamaterials are engineered structures with properties not found in nature. They enable negative refractive indices and other exotic electromagnetic behaviors. These materials are essential for bending electromagnetic waves around the. Hence, these metamaterials are the structures with the properties which are not found in nature, and they enable the negative refractive indices, and these materials are essential for bending the electromagnetic waves around the objects. Transformation optics. Transformation optics is a mathematical framework used in designing cloaks. It involves transforming electromagnetic fields via coordinate mappings. This approach guides the development of materials that steer light along desired paths. Types of electromagnetic cloaks. Invisibility cloaks can be classified into spherical, cylindrical, and planar types. Each type is suited for specific applications and frequency ranges. Researchers are exploring active and passive cloaking strategies. Materials used in cloaking devices. Metamaterials are typically composed of periodic arrangement of conductive elements. They require precise fabrication at sub-wavelength scales. Losses and bandwidth limitations are challenges in material design. So here we can see in the right side picture the electromagnetic spectrum, where the sources are AC power, television, telephone, satellite, sunlight, light bulb, medical X-ray, radioactive sources. These are the sources of the electromagnetic spectrum. Coming to the radiation type wavelength, here we can see radio waves, microwaves, infrared, ultraviolet, X-ray and gamma rays. Depending upon the wavelength, there are some of the radiation type. Here in the last we can see the approximate scale of wavelength. This is the scale in 10 power minus 4 to 10 power minus 5. There will be the visible light. So in this wavelength we can see buildings, humans, butterflies, needle points, protozoans, molecules, atoms and atomic nuclei. This is the electromagnetic spectrum. Design challenges. Achieving broadband cloaking remains a significant obstacle. Material losses can degrade cloaking effectiveness. Scaling cloaks for practical real-world objects is complex and costly. Experimental demonstrations, several proof of concept cloaks have been successfully built and tested. Early experiments focused on microwave frequencies with limited bandwidth. Recent advancements aim to extend cloaking to higher frequencies and broader spectra. Applications of electromagnetic cloaking. Defense and military concealment are primary drivers of research. Stealth technology benefits from cloaking to evade radar detection. Potential civilian uses include privacy, non-invasive sensing, and antenna design. These are some of the applications of electromagnetic cloaking. Limitations of current cloaking technologies. Most cloaks are narrowband and only work at specific frequencies. Complete invisibility, especially across the entire spectrum, remains unachieved. The complexity and cost of fabrication limit widespread practical use. Future directions in cloaking research. Researchers are exploring active cloaking that can adapt to changing environments. Integration of cloaking with other technologies like sensors is investigation. Advances in nanofabrication may enable more efficient and versatile cloaks. Ethical and security considerations. Cloaking technology raises concern about privacy and misuse. Potential Potential for Clandestine activities necessitates regulation and oversight. Responsible development is essential to balance benefits and risks. Comparing electromagnetic cloak with other cloaking methods. Optical and acoustic cloaks are alternative approaches with different challenges. Electromagnetic cloaks specifically target electromagnetic wave manipulation. Each method requires distinct materials and design strategies. Role of computational modeling. Simulation tools are vital for designing and optimizing cloaks. They help predict electromagnetic behavior before physical fabrication. Advances in computational physics accelerate cloaking research, commercialization, and market potential. Currently, cloaking remains primarily in the research and development phase. Potential markets include defense, telecommunications, and privacy solutions. Commercial viability depends on overcoming technical and cost barriers. Recent breakthroughs and innovations. Researchers have developed cloaks with the reduced losses and wider bandwidths. Novel metamaterial designs have improved flexibility and performance. Integration with other optical devices is creating new possibilities. Coming to the summary and key takeaways, electromagnetic cloaking manipulates light to hide objects from detection. Materials, metamaterials, and transformation optics are foundational technologies. Despite progress, practical, broadband, and cost effective cloaks are still under deployment. Conclusion and future overlook. The field continues to evolve with promising technological innovations. Achieving practical full spectrum invisibility remains a significant goal. Collaboration across physics, engineering, and material science will drive future breakthroughs. Thank you.